In this problem, we have two charged capacitors that are connected together, and we want to find the total energy stored in one of the capacitors at equilibrium. So we'll do our picture before. We have two individual capacitors. I'll put the positive plate on top, the negative plate on the bottom, and this will be our 6 microfarad capacitor charged to 50 volts. And the second capacitor has a capacitance of 4 microfarads and it's charged to 34 volts. So that's the before. After, these two are now connected, positive to positive and negative to negative. Now it's very important that you make a note of whether or not they're connected positive to positive or negative to negative, because if they were connected positive to negative and vice versa, then the total charge would be the difference between the two charges. If they're plus to plus, the total charge is the sum of the two charges. So this is after. The capacitance doesn't change as a result of being connected, so that's still a 6 microfarad, and this is still 4 microfarad. But now these are going to have a different charge. I'm going to call Q3, Q4. Over here I'm going to calculate Q1, which is CV. So this would be 6 times 50 is 300 microcoulombs. Q2 would be 4 times 34, which is 136 microcoulombs. The total charge before is the sum of these two quantities, 300 plus 136, for a total of 436 microcoulombs. Now, because there is no battery involved in this problem, there is nowhere for that total charge to go, and so the total charge over here must also be 436 microcoulombs. And that is going to be the sum of Q3 plus Q4. Now, once these are connected together like this, they're actually in parallel, and so the voltage across each of these capacitors must be exactly the same in this after picture. So the voltage after is equal to the charge over the capacitance. And so this must be, for each of them, Q3 over 6 must also equal Q4 over 4. So this gives us two equations with two unknowns, Q3 and Q4. I'm going to substitute one of the equations into the other so that I have Q3 over 6 must equal 436 minus Q3 over 4. Solving for Q3, I get 262 microcoulombs. Now we're only interested in the energy across the 6 microfarad capacitor, so we don't even need to calculate Q4. We can go right ahead and get the potential energy stored in the 6 microfarad capacitor, which would be 1/2 Q3 squared over C. So it's 1/2 of 262 microcoulombs squared over 6 microfarads, which gives us 5.7 millijoules.